Welcome to Energy Talks, a regular podcast series featuring expert discussions on power system testing, data management, cybersecurity, and important trends in the power industry. My name is Scott Williams from the podcast team at OMICRON, and I will be your host. Hello, everyone. Bushings may look like simple low-cost transformer components, but they are among the most critical assets in the high-voltage network. Statistically, around 40% of all transformer failures involve bushings, often leading to catastrophic consequences like fires, explosions, and widespread grid outages. Joining me in this episode to discuss this topic are two OMICRON product managers and bushing testing experts, Rothleitner and Jakob Hämmerle. They will highlight the importance of bushing diagnostics to catch early signs of bushing degradation caused, for example, by moisture ingress and insulation aging, whose warning signs are often difficult to detect easily with individual 50 or 60 Hz tests. To meet this diagnostic challenge, Hannes and Jakob will describe how the industry is shifting toward multifaceted diagnostics, using a combination of various testing methods, including tan-delta, dielectric frequency response, and voltage sweeps, to expose these hidden flaws early. They will share practical tips for troubleshooting testing challenges and offer us a glimpse into the next 10 years of bushing diagnostics with the emergence of newer resin insulation technologies and the use of artificial intelligence, or AI, for data interpretation. More specifically, they will explain why the future is not about more data, but about high-quality interpretation to support better decision-making. So without further delay, hello, Hannes and Jakob. Welcome to Energy Talks.
Hello, Scott. Nice to be here.
Hey, Scott.
Well, thank you for taking the time to talk about this topic with us. At first glance, bushings appear to be a relatively simple component of a power transformer. Nevertheless, why are they considered to be one of the most critical components in the high-voltage network?
The reason lies in the failure characteristic and, more importantly, in the consequence of a failure. Statistically, around 40% of all transformer failures involve their bushings. What makes this particularly critical is that these failures often have serious consequences. They can lead to arcing, fire, or even explosion. This is what sets bushings apart from many other transformer components. A single bushings failure can escalate and risk the entire asset.
Thank you, Hannes. Can one of you give us a practical example that illustrates this?
Sure, Scott. So, a recent incident shows just how quickly this can escalate. In March 2025, there was a major fire at the Northlight substation near the Heathrow Airport. The event started with a failure in high-voltage equipment, but the consequences went far beyond the substation. According to the investigation, the probable root cause was moisture ingress into a high-voltage bushing. Moisture ingress means that moisture entered the insulation system, and over time, this can lead to an electrical fault. In this case, the result was a serious fire, a widespread power outage, and the closure of one of the busiest airports in the world for 18 hours. Now, we have to be careful here. The airport disruption was not caused by the bushing alone. The final impact also depended on grid operation, redundancy, and the resilience of the connected systems. But that is exactly the point. A bushing may look like a small component compared to the transformer itself, and it may also represent only a small part of the total asset cost. But when it fails, the impact can be much bigger than the component itself. That is why bushings are treated as critical components in the power system.
Thank you, Jakob. Hannes, what are the most common failure modes then encountered in practice, and why are they often difficult to detect?
Yes, I can give you an overview. So, insulation aging, moisture ingress, thermal overheating at contacts, and defects inside the condenser body are the most common ones. Mechanical stress like vibration or seismic events can also trigger failures, and environmental conditions can also accelerate the whole process. What makes these problems difficult to detect is that they often start small. The bushings may still operate as usual, while the warning signs can be very weak. For example, moisture may first appear only at small changes in tangents delta, overheating may only be visible with infrared scanning, and internal electric defects may stay hidden until partial discharge or a sudden breakdown appears. Another challenge is that different mechanisms overlap. So one symptom can have several causes. That means a Bushing can look stable in one test, while a deeper problem is already developing. So to sum it up, the most common failures are usually slow, hidden, and can have different causes.
And this is exactly where dielectric diagnostic methods become important. A good starting point is often a dissipation factor or power factor measurement, usually at the mains frequency, 50 or 60 Hertz. But we can also look at the insolation over a wider frequency range. This method is called the dielectric frequency response, or simply DFR. Depending on the application, different OMICRON devices can be used. For example, the CPX200 with the HVX10, or the CPC100 with the CPTD12, or DIRANA, which is designed for measurements over a wide frequency range. These devices help us to detect changes in the insolation at an early stage. In other words, they show us when the dielectric behavior starts to change, and that gives us a chance to act before a small defect becomes a critical failure. But there's one important point. A reliable assessment should not be based on one method alone. It should combine several diagnostic approaches, such as dissipation of power factor trending at mains frequency, DFR, visual inspection, and in some cases, Bushing oil analysis. Each method adds value, each method sharpens the picture, and together they give a much better view of the asset condition. At OMICRON, our role is to support users, especially with dielectric tests. That means helping them to perform the measurements correctly, to interpret the results, and to use them as part of a wider diagnostic strategy.
Hannes, why is a single measurement at mains frequency often not sufficient to reliably assess the condition of a bushing?
Many Bushings problems only become visible when you look at how the Bushing on the insolation of the Bushing responds over a range of frequencies. Therefore, DFR is used to distinguish effects like moisture, aging, and even contact problems that may look similar or stay hidden in a single test point. One of the main advantages of modern test devices is their selectable output frequency, and so that these tests can be performed without any additional efforts.
This raises an important question. How can we gain a more complete picture of the insolation condition? Jakob, could you tell us about that?
Yes, Scott, that's really important. And the point is, by measuring not only at a single frequency, but the dielectric response within a frequency range, the user gets results which can reveal insolation defects more clearly and in earlier stages. At mains frequency, these effects are often hard to spot. The insolation is probably already heavily degraded. This is why conventional 50-60 Hz measurements are often complemented by narrowband or wideband DFR measurement. The key benefit is not just more data, but the meaning behind it. The ability to separate different loss mechanisms across the frequency spectrum, which provides much deeper insight into the insolation condition. It's also worth mentioning that some types of defects cause a voltage dependency in the results. That's why testing with varying voltage can have an additional diagnostic value and is therefore included in our test plans as a so-called voltage sweep.
Thank you, Jakob. Hannes, what role do trending and experience play compared to threshold values?
Yes, trending can be a very powerful tool. So a Bushing can remain within a specified limit for years while still gradually moving towards failure. This is why trending is often more revealing than a single limit. For instance, the threshold values provided by SIGRE can be quite handy. They provide guidance to identify when certain actions are required. But as said, warning signs in early stages may be tolerated or even not detected. And in some cases, these thresholds at different frequencies can give contradicting assessments. A reliable condition assessment is therefore typically based on several factors: absolute limits, long-term trending, engineering experience regarding the bushings, design, type, age, and operation condition. Because the same measurement value can have different meanings, for instance, depending on the bushing's technology.
Jakob, how are these diagnostic principles implemented in practice with measurement devices? Can you give us an overview and explain where each OMICRON solution has its strengths when it comes to Bushing diagnostics?
Yes, Scott, let me try to give you a short overview because we are using several complementary systems. The CPTD12 and TD15 are established solutions and are used by experts all over the world. They are highly integrated into our transformer testing workflows, making them a great solution when working with the primary test manager software. And main devices such as the CPC100 or Testrano 600. They can perform voltage sweeps up to 12, respectively 15 kV. They have a frequency range from 15 to 400 Hz. And with this, already many bushing defects can be detected. A new addition to the portfolio is the CPX200 combined with the HVX10. With an output voltage of up to 10 kV, standard 50-60 Hz testing and voltage sweep measurements are easily possible. For bushings, the increased frequency range from 1 to 600 Hz provides additional diagnostic value, and with its 4 inputs, one for each bushing, ladder trips are minimized. And of course, the 10 kV DC from the same output speeds up power transformer measurements in general.
Yeah, and I can also give a little bit of insight in what the DIRANA is doing. The DIRANA is our specialized solution for broadband DFR testing, since the output signal can have almost every frequency between DC and 5 kHz. For bushings, this can be especially useful when a deeper diagnostic insight is needed, particularly for assessing moisture in oil-impregnated paper bushings. Another advantage is the small size and weight, and based on that, the higher safety level. A growing trend in the market and also an application area for DIRANA is wideband DFR testing. So you are performing tests on bushings down to 10 mHz or even 1 mHz. The goal by doing this is to obtain a dielectric fingerprint response early in the life of an asset, which acts as a reference for upcoming measurements.
Thank you both for that overview. Staying with you, Hannes, so is the main advantage of frequency response analysis simply that it provides more information?
The main advantage is not just more information, but more diagnostic value. It helps to separate different defect types. A mains frequency test gives only one value, but frequency response analysis shows how the bushing behaves over a range of frequencies, which makes hidden or mixed problems easier to identify.
So we've talked a lot about measurement methods and interpretation, but when moving into real-world applications, what about implausible or inconsistent results? Jakob, for example, there's negative dissipation factor. What does that actually mean? Is it a physical effect or a measurement issue?
A negative dissipation factor would indicate that the resistive losses in the measured insulation are negative. In other words, that the insulation would be acting as a source of energy. This is, of course, not physically possible. It therefore typically indicates a measurement or setup-related issue. In field setups, certain influences can distort the measurement signal.
So, Jakob, does that mean such effects occur in the field more often than expected?
Yes, probably more often than one would typically expect. The test setup is very important to obtain reliable setups. So possible root causes can include bad measurement contacts, improper guarding, or high surface leakage currents, so for example, dirty bushing. Fortunately, in almost all cases, these issues can be resolved by improving the setup. For example, by improving the connections, especially the grounding clamp, by cleaning the bushing surface directly before the measurement, or a lot of other smaller tricks. And if required, our 24/7 technical support has the competence and even more suggestions to directly support the user during a measurement in the field.
Well, and Jakob, I can see two reasons for that, right? So first of all, almost every test on site is a bit different. The asset design, the voltage level, and the different types of connectors make it difficult to always use the exact same setup. And the bushing itself is a large, unshielded structure, so electromagnetic interference is a bigger issue than at dielectric tests on other isolation systems. And of course, weather conditions also have an influence. Secondly, there is still a lack of standardization. The frequency range, test voltage, and testing techniques are not fully harmonized across the industry. This can lead to differences in results and further in interpretation.
Thank you, Hannes. Jakob, how do you deal with contradictory or implausible results?
Well, Scott, I think the key point here is don't jump straight to the asset. In practice, the first step is always to check whether the measurement itself is plausible. That means looking at the complete setup, grounding, guarding, cable routing, and the reference potential. Only when these influences have been ruled out should we start evaluating the asset itself. So, In field diagnostic, the first question is not what does the measurement show? The first question is under which conditions was this measurement taken?
Very good point. So, Hannes, does more frequency information automatically lead to better decisions?
Well, I would say not automatically. So one could say that more frequency information translates to higher physical resolution. So a deeper view into different polarization and conductivity mechanisms. This helps to better distinguish the already discussed effects. So I would say that measuring with a bigger frequency bandwidth adds diagnostic sensitivity and also simplifies pattern recognition. This is very important. However, without a solid physical model and practical experience, additional data can even lead to misinterpretation.
Interesting. So, Hannes, where do you draw the line between useful complexity and over-engineering?
I would say the limit is reached when additional measurement information no longer improves decision-making quality. If a method provides more data, but that data can no longer be translated into clear condition statements, then it stops adding value and only increases complexity. In practice, decision makers, such as asset managers, want to understand if the bushing is healthy or needs to be replaced, and if so, how soon. So the key criterion for them is not how much you can measure, but whether the results enables clear decision-making.
Thank you, Hannes. Jakob, if you were to summarize everything, where is the highest practical value in bushing diagnostics today?
Well, the highest practical value, I think, is in early detection, especially for common degradation mechanism that develop slowly over time. So, for example, moisture ingress, aging, or interfacial processes in the bushing layers. For that, classical methods such as the dissipation or power factor measurements at the 50-60 Hz mains frequency are still essential. They provide the reference baseline. But DFR adds another layer of insight because it makes frequency-dependent effects much more visible. Ultimately, the real strength does not come from a single measurement method. It comes from combining reliable field measurements, proper trending, and physically sound interpretation of the results.
Hannes, in your opinion, where is bushing diagnostics headed over the next 10 years?
That is a really tricky question, I would say. There's still a lot to be done, especially in standardizing how results are interpreted. While oil-impregnated paper bushings are well understood in terms of aging behavior, this is not yet the case for newer technologies like resin-impregnated paper or resin-impregnated synthetics. For them, we still lack a clear link between dielectric changes and derived condition statements. So basically, what certain dissipation factor variation over frequency tell us for the actual condition. Another interesting topic is the use of AI and machine learning in diagnostics. In the future, these methods may help combine measurement data, test history, and asset-specific information into better evaluation. I would say building robust models and gathering enough training data for them are the challenges ahead. And finally, field usability will remain important. Diagnostic methods must be not only accurate, but also reliable under real operation conditions, which will continue to drive improvements in test procedures and workflows.
Thank you, Hannes. So it's less about how much data we can generate and more about how confidently we turn it into decisions. Is that correct?
Yes, exactly. I would say this is exactly what we are discussing here and what is the point. In the end, it's not about producing as many measurements as possible. It's about detecting critical changes early enough to prevent failures and being confident enough in the interpretation to act on them. And that's where the true value of bushing diagnostics will continue to lie in the future.
Well, that's a great closing thought. Hannes and Jakob, thank you for sharing your insights into the world of bushing diagnostics in this episode of Energy Talks.
Thank you very much, Scott.
Thank you for having us.
And a big thank you to our audience for listening to this and other episodes of Energy Talks. We always welcome your questions and feedback. Please send us an email to podcast@omicronenergy.com. OMICRON has several years of experience in power system testing, data management, and cybersecurity, and offers a matching solution for your application. For more information, visit our website at omicronenergy.com. Please join us for the next episode of Energy Talks. Goodbye for now, everyone.